It is, support very faculty. এই শোনো, তোমার কাছে কলকিং তোমার কাছে গ্রুপ আছে তোমাদের ডিপার্টমেন্ট মেম্বার্স ডিএ এর কিছু আছে? কি আছে? ডিএ এর কোনো ফ্যাকাল্টি গ্রুপ আছে হোয়াটসঅ্যাপ যেখানে মেসেজ করবে টু অ্যাটেন্ড দ্য প্রোগ্রাম? We have the sleeper.
There's a building in Pondicherry, near Pondicherry.
Ooh.
And
Correct.
Okay, we have a decent quorum for the start, so let me actually begin. So welcome back to a fresh set of NSF Wednesday Colloquium series for this year. I wish all of you a very happy new year. I hope it's all productive and all of you are healthy throughout the year. It's also a point where we are trying out something new for the Colloquium series for the first month. I'd like to reiterate that we want all of our NSF members, faculty, students, staff to attend the colloquium in person. And that's sort of a trial. What we are trying to do is we are going to not let people join by Zoom. Only people who are outstation can join because if they are missing the colloquium. But that's one of the few steps we are trying to take. Also, I'm taking new fresh suggestion for speakers. And it would be good if you have thoughtful suggestions. That's something that will work for all of us. So without further ado, it's actually great to have Professor Andrew Orr-Ewing amongst us in this room. After a lot of very interesting dynamics with the DAE. I hope that he gets a chance to visit the labs today, gets to see the science that we are doing. And if anybody wants to meet him, you guys can please tell us. He's not here for a long period of time, just for today, but it would be good if you are interested after the talk. I just wanted to tell Andrew that this is actually pretty historical for all of us. This was started by our founding director, Professor Homi Bhabha, this event. It brings in all the faculty members from different quarters in the natural sciences faculty, both physicists, chemists, and biologists. They have a good time listening to a broad talk, and that allows them to sort of mingle with ideas. So, and it has trained students over the years. So, I'm very happy that you're joining us today for this, and I look forward to your talk. But before that, I would request Professor Shudipto Maiti from our department to formally introduce Andrew.
thank you, Jyoshman. It's a pleasure introducing Professor Andrew Orr-Ewing from the University of Bristol. And Andrew started his educational career in Oxford, where he both did an undergraduate degree and a PhD, and then went to Stanford to work with a person who was online here yesterday for one of our talks, Dick Zare. Okay, Richard Zare is one of the most well-known chemists that's still active. And so he worked with Richard Zare for a few years as a postdoc, and then, of course, came back to the UK. And he has blazed a trail of understanding fundamental reactions in the gas phase as well as in the solution phase of ions, radicals, small molecules, including I spotted some biomolecular stuff. Is it okay? So he's an ultrafast spectroscopist. So he looks at reactions starting from the first few femtoseconds and look at what happens, what is the mechanism of where does chemistry happen. Remember, femtochemistry in the late 80s was all the rage, and one by one, people could put together the quantum mechanics that you can calculate and with the spectroscopic outcome that you record in the lab. So he is really a flag bearer of that, but he has gone further. So he has gone further to understand for these small molecules, radicals, etc., which are really, let's say, some of them are UV excitable, and those are really very relevant in the atmosphere, especially in the upper atmosphere. So he is an ultrafast spectroscopist who is applying all that to a very relevant problem of ours, which is the atmosphere, understanding the reactions in the atmosphere. He was looking through during the lunch outside and looking at the haze and says, okay, I can tell you a little bit about that. Okay, so we're all waiting to hear from him, but let me just finish by saying, of course, this very well-decorated scientist, he has been getting prizes, I think, since about the time of his postdoc or early career, which I just mentioned one, 2017, he was elected as the Fellow of the Royal Society. And we are joking about signing on the same book where Isaac Newton and Einstein have signed. And that's quite something. So we welcome Professor Andrew R. Ewing. Andrew.
Sudipta, thank you very much for a very kind introduction. And thank you ever so much for inviting me to come here. I had the pleasure of visiting TIFR probably about 8 years ago. I didn't check the exact date. It was much easier to get in then. I have to thank also Jyotishman for the unnecessary work I created by wanting to come here and actually come inside the building. So this generated a lot of extra work, and I do apologize, but thank you so much for enabling this visit. It's a great pleasure to be here. I happen to be in Mumbai. It's fantastic to be back in Mumbai as well. But thank you both indeed for coordinating and enabling this talk. What I would like to talk to you about today is going to be laboratory studies of processes of importance in atmospheric aerosols. So I think I have to apologize also at the start that we don't use the TIFR balloon facility, which I learned about today, which does measure upper atmosphere and high altitude particles. We're not doing that. Everything I'm going to tell you about is laboratory-based studies. And I'm going to tell you two types of story, two very different techniques that we're using to study different phenomena that are important in relation to aerosol science. But let me start by just spending a bit of time telling you what I mean by an aerosol and what aerosol science really corresponds to and how it relates to atmospheric processes. So let me start just with this picture here. Some of you may recognize this. This is the Amber Fort in Jaipur. So I was fortunate to visit there about 7 years ago. And I have much nicer photographs than this. It's a magnificent place. But I chose this picture because it's taken from a place called the Jaeger Fort, which is above the Amber Fort. And you can see in the background, well, you can't really see the background. That's the point. Back here, there is this haze. And this is a particular problem in cities like New Delhi at the moment. There's a bit of haze in Mumbai. It's not unique to India. Cities around the world have these hazes. And these hazes, this poor visibility, is a consequence of very small particles dispersed in air. And when you have a distribution of particles in a gas, we call that an aerosol. And this distribution of particles might be solid particles or it might be liquid droplets. But that's what we mean by an aerosol. So it's the whole phase, it's a whole combined phase of the particles and the gas. So I'm going to talk about aerosol particles, by which I mean the solid or liquid particle dispersed in air. And I'll talk about aerosols more generally to mean the combined particle and gaseous medium. But these particles, the origin of these particles, certainly in northern India, as I understand it, at this time of year, perhaps earlier, is related to burning of crops, so fields. So the harvest is taken in, you leave behind what I think you call as well the stubble. In Britain, we certainly call it that. And then farmers set fire to the fields to burn away the residual plant matter. And that creates this air pollution. And we used to do this in the UK. When I was young, I used to watch the farmers do this to fields, and I was amazed that they could control the burning of their fields, but they somehow did. But we don't do it anymore in the UK. But it happens here, and it creates these hazes of particles in the air, and there are consequences for poor visibility, but also for health, because if you're breathing in these particulates and they penetrate deep into your lungs, there are serious health concerns related to that. So I'm not going to tell you how to solve this problem. That's way beyond my pay grade, but I will just talk a little bit about some of the types of properties of these particles that we can study in the laboratory. I should have said at the start, I'm very happy to be interrupted. If anything I say is unclear, please do interrupt me. I don't mind at all.
Actually, we will let you go for 15 minutes.
Right, and then lay in.
Non-experts.
Right, and if we lose time at the end and I have to cut some material, that's fine. Right, so let me just tell you a little bit more about atmospheric aerosol particles. So these particles come from many different sources. So here are some examples. Here is, let me just get used to your pointer as well. Here are ocean waves breaking, and these generate what's called sea salt aerosol. The ocean spray ejects water with sodium chloride in it into the atmosphere, and you generate sodium chloride or sea salt aerosol. So that's a very large source of particulates in the atmosphere. Then there are processes like volcanic eruptions. So you can see here soot particles, mineral particles being ejected from a volcanic eruption into the atmosphere. But volcanoes do more than that. They emit sulfur dioxide, and sulfur dioxide forms SO3 in the atmosphere. It oxidizes to SO3, and SO3 then condenses, forms sulfuric acid, and you generate what's called sulfate aerosol. So there's a lot of sulfate-based aerosol in the Earth's atmosphere. Here's biomass burning. So this is, sorry, I'm pressing the wrong button. That's why it's not. Let me go back. Here down here is an example of particulates generated from burning of plant material. So as, for example, comes from these crop burnings. So you can see here the flames and the plant material. But if you look up here, you can see these soot particles that are being ejected. Now, those particles are often carbonaceous, so they're soot-like carbon-based materials, but there are also particles made of organic molecules. So partially combusted organic material also escapes. And that's known as brown carbon, and that's going to be what I'm going to focus on today. But I will come back to that point in a little while. Let's just look at some more sources of atmospheric aerosol. Here is, for example, wind-blown dust from deserts, such as the Sahara Desert, that distributes minerals into the atmosphere. And then if you can see this picture, this is a smokestack. So this is human activity from industrialization and from transportation, which generates particulates that are ejected into the atmosphere. And then there are natural sources like pollen grains, which are examples of natural sources of aerosols. So there are very rich source and very diverse sources of these particulates in the atmosphere. So please don't think of the atmosphere as just being all gas. There are all these particles distributed in the atmosphere as well, and they lead to things like cloud formation. So water condenses on these particles. So we call them cloud condensation nuclei because they condense water and you form cloud cover. So here's why we care about these, particularly in the current day and age. This is a plot from this report here. So IPCC is the Intergovernmental Panel on Climate Change. And they are the people who are assessing the effects of human activity on climate and condensing together all the scientific literature to help politicians understand the impact of what we're doing on future climate. So you can see here, this is a plot of what's called radiative forcing. So that's this title at the top. So radiative forcing is a quantification, it's a measure of how some component of the atmosphere, a gas or a particle, how to the extent to which that component of the atmosphere traps the energy from sunlight. So species that have positive radiative forcing are things like CO2. So CO2 is a well-known greenhouse gas. So it's leading to a net warming of the atmosphere. So it has what's called a positive radiative forcing. And so the way that works is light comes from the sun, it penetrates through the atmosphere, it warms the Earth's surface, and then the Earth's surface, as it's warmed, radiates in the infrared. So the warm Earth's surface is an infrared emitter, and that infrared is radiated back towards space, but it doesn't escape the atmosphere because it's absorbed by the CO2. So the CO2 traps that energy in the atmosphere, and we call that a positive radiative forcing. So there are various well-known greenhouse gases. So CO2, methane, nitrous oxide are examples of long-lived long-lived greenhouse gases. And these bars here show the extent to which they contribute to warming of the atmosphere. So the extent to which they act as greenhouse gases. And that's relatively well understood. If you look at the uncertainties relative to the magnitudes of those effects, they're relatively small. The emissions of greenhouse gases are well understood by climate scientists. Then there are various other gases here, chlorofluorocarbons and hydrofluorocarbons, gases that are used for things like refrigeration and foam blowing. CFCs are now illegal to use. They've been phased out because they deplete stratospheric ozone. But then we come to this box down here that I've drawn in red, outlined in red. And this box encompasses the effects of particles, aerosols in the atmosphere. So there's sulfate aerosol, there's organic carbon, which I'll talk about in a bit. There's black carbon, that means soot particles, and there are other particles formed from gases like ammonia. And these have really quite a substantial effect on climate. And I'll talk to you about the mechanisms for that in a minute. But you can see sulfate aerosol, for example, has a net cooling effect in the atmosphere. And that's because particles of sulfuric acid higher up in the atmosphere actually are quite reflective to sunlight. So the sunlight that comes in from space is scattered back into space by particles like sulfuric acid particles. And so they have a net cooling effect on the atmosphere. So we say they have a negative radiative forcing. But look at the error bars on that. The error bar is very large. So that's the uncertainty and if we look at some of these other species, so these organic carbon and these black carbon species, these are absorbing particles. These absorb sunlight. And so they trap sunlight in the atmosphere and warm the atmosphere. And so they can have some contribution they can have is a warming on the atmosphere. And that in some cases, it's not clear whether overall they warm the atmosphere or cool the atmosphere. So establishing a better understanding of how these particles act on the atmosphere is really quite important for predictions, reliable predictions of future climate and future temperature. And so one of the points raised by this IPCC report is that we need to have better characterization of how aerosol particles behave in the atmosphere if we're going to have robust predictions of future climate. And that's what I'm going to talk to you about today, is how we might not how we can solve that problem, but how we might address it. So how do aerosols actually affect the atmosphere? It's tremendously complicated, but we can break it down into two main effects. What's called the aerosol direct effect in this top box up here, and then the aerosol indirect effect in the box below. So the direct effect is what it sounds like. Sunlight comes in, it encounters these particles in the atmosphere. If the particles absorb the sunlight, that has a warming effect. And if they reflect the sunlight back to space, that's a cooling effect. So the balance of those, the absorption and the scattering back to space, determine how these aerosols affect the temperature of the atmosphere. The indirect effect is more subtle. The indirect effect is a recognition that these particles affect the amount of cloud cover over the planet. Because you condense water on these particles, if you have a lot of particles in the atmosphere, say sea salt spray, that can lead to increased cloud cover. And anyone who's been in an aeroplane knows that the tops of clouds are very bright. They look bright white. That's because they're reflecting sunlight back. So these tops of these clouds are highly reflective. They increase what's called the albedo of the Earth, which is the reflectivity of the planet. So they reflect more sunlight out to space, and so they have a net cooling effect. But understanding how aerosol particles lead to cloud cover is really quite complicated. And so that's a major source of uncertainty in how these aerosol particles affect the Earth's atmosphere. They also have more subtle effects, like they affect the amount of precipitation. So they affect the cloud lifetime. The larger the water droplets are that form in the clouds, the more prone they are to rain out and disappear. So cloud lifetime is another effect that depends on aerosol particles. And cloud altitude is also affected by these particles. So all those are tied together in what's called the aerosol indirect effect. And both those direct and indirect processes need to be understood better. I'm going to focus today more on the direct effect than the indirect effect, but both of those are very active areas of research. So why is there still so much uncertainty about what these aerosol particles are doing? Well, what it comes down to is that the types of particle we have in the atmosphere are tremendously complicated. There are huge ranges of size and shape and so composition of these particles and phase of these particles. They're not all just uniform liquid drops. If they were, life would be much simpler for us to understand. But they come in all sorts of shapes and sizes, which you can understand from the different sources that I talked about a little earlier. So, for example, they come in a variety of sizes. So these particles might be anything from, say, a few hundred nanometers in diameter up to tens of or hundreds of microns in diameter. So they can be a wide range of sizes. They can have a variety of different compositions. So they might be largely aqueous, or they might be minerals, mineral dust, or they might be sulfuric acid particles. They come in lots of different shapes and sizes. So crystalline particles tend to be more cubic, for example, in morphology, whereas droplets tend to be spherical, but they come in fractal geometries as well. If you look at these soot particles from combustion under a microscope, they have fractal structures, and they can be mixed phase as well. So, and there are various forms of mixed phase geometry structures that you can have. So we have a tremendous complexity associated with these particles, and that leads to real challenges to study their properties. I'm going to focus today exclusively on droplets that are spherical and homogeneous. Let's keep it simple. And if we're working with spherical and homogeneous particles, we can use a theory to understand their optical properties known as Mie theory. So Mie theory treats the interaction of light with these particles. And we can, if we know certain properties of the particles, then we can use this Mie theory to describe completely their absorbing and scattering properties. And we can then understand their impact that they will have on climate, on radiative forcing. And what we need to know to understand or to be able to predict the properties of the particles, if they're spherical and homogeneous, yeah.
By homogeneous, do you mean the density of the particle or the distribution of particles within the medium?
So what I mean is that the material they're made up of is uniform throughout. So
Within one particle?
yes, within one particle, yes.
There's one more.
Yeah.
In your previous slide, you talked about the direct and the indirect effect. So I just wanted to understand that by direct, you are including both the sun rays coming from outer space onto the particles, but also re-radiated infrared as well. Both of them you're categorizing under the direct.
Yes.
Right? Okay.
So the overall radiative forcing depends on the net change in energy trapped in the atmosphere. So you have to include both those effects. Yes. Yeah. All right. So what we need to know about these particles, if we want to describe their properties completely, we need to know what's known as their refractive index. And the refractive index is this thing here. Oh, sorry, I will get the hang of this in a minute. Is this property M here, and M is the refractive index. It has two parts to it, so it's a complex function. So the real part of the refractive index is N, and the real part is essentially tells you how the speed of light changes in the material. So it's the ratio of the speed of light in vacuum to the speed of light in the material, and that leads to the scattering properties. It's what leads to refraction in a dense medium, for example. So that leads to scattering of light. And the complex part is denoted by K, and that controls the extent to which the particle absorbs light. So a dark black medium, a particle, has a large value of K, and a transparent water droplet has a low value of K. So this is a measure of how strongly absorbing those particles are. So if we know those two properties, then we can predict anything we want to know about the interaction of these particles with light. We have to bear in mind that these properties will depend on wavelength. So the light that these particles absorb depends on the wavelength, and the refractive index also changes. The real part also, it depends on the wavelength. So we have to bear that in mind, but that's an additional level of complexity we can worry about later. So I'm going to focus today on trying to understand what's known as brown carbon aerosol. So brown carbon aerosol is formed by combustion of plant matter. So I'm not a biologist or a plant scientist, but I understand that a lot of the structural elements in plants contain phenolic compounds. So these are these aromatic rings, these six-membered carbon rings with OH groups attached. So you get these phenolic compounds. And when you burn these materials in air, you release these phenolic compounds, and at the high temperatures in the flame, they react with nitrogen oxide compounds in air, and they form what are called nitroaromatic compounds. So these are characterized by having these, what's called an aromatic ring. I don't know how many of you are chemists and how, but I'm assuming some of you aren't and may not be familiar with the notion of an aromatic ring. But these are six-membered carbon rings, such as benzene and toluene and phenol, contain this functionality. And then they have this OH group in it, this alcohol group, and they have a nitrogen dioxide group. And so we call these things nitroaromatic compounds. This is called nitrophenol, and then we have various others, nitrocatechols and 2,4-dinitrophenols. And these are also well known to be very persistent pollutants in the environment. So if they're released by human activity, then they hang around for a long time in the environment and they're toxic in the environment. But they also form naturally by this combustion type process. And so I'm going to talk to you a little bit about how we can study the properties of these nitroaromatic compounds in aerosols. And I'm going to break this down into two parts if I have enough time, but if I run out of time, we'll just skip the second bit. We're studying these in two ways that have almost accidentally converged in my lab. We had two projects running that were very distinct, and they've ended up focusing on the same big scientific question, which is a curiosity for me at least, but it's just the way things have worked out. I'm going to talk to you first of all about how we can measure the light, the extent to which these particles absorb light. So we can quantify this complex part of the refractive index, this K value, more precisely. And then if I leave myself enough time, I'll talk to you about how we can study what happens inside these aerosols once the light has been absorbed. So there are two steps here. First of all, you absorb the light, then what happens? And we'll see how far we get. So let's focus on how we can measure how these particles absorb light. So let's suppose we take I'm not going to take a sample of aerosol from the atmosphere. It's way too complicated for me to study that. I'm going to work on a very well-defined, controlled, laboratory-generated droplet. And I want to work on one droplet at a time. Because if I work on, say, 1,000 droplets in an experiment, then those 1,000 droplets are not all going to have the same size. And their properties depend on their size. So we need to narrow this down to one droplet we really characterize very well if we want to understand what's going on. So we're going to do single droplet experiments. And we're going to work on droplets that are about 1 or 2 microns in diameter, so very small. So that presents a challenge. We need to measure their optical properties, how much of light they absorb, but they're only about 1 micron in diameter. So we need a very sensitive spectroscopic technique to measure that very small amount of light these particles absorb. And we use a technique known as cavity ring down spectroscopy to do that. So I'm going to explain to you quickly how that works and then show you how we can use it in combination with an aerosol project to measure the properties of the aerosol particle. So the idea here is if I take a sample and I shine light through it, the amount of light that's absorbed depends on the concentration of the absorbing species in my sample, and it depends on how far the light travels through the sample. So the longer the sample is, then the more absorption you get. But I've limited myself to working with a 1 micron diameter droplet. So I only get 1 micron of path length through the sample, unless I send the light through the sample and then send it back again and back again and back again and do it lots of times. So I multipass, I send the light through the sample numerous times, and that amplifies the amount of light that's absorbed. And so in this cavity ring down technique, that's what we're doing, but we take it to an extreme where we trap the light here. Whoops, I really would. We trap the light between 2 mirrors, And we use mirrors that are better than 99.99% reflective. And if you do the maths of this and you take two mirrors and you put them a meter apart, then the distance the light will travel between those two mirrors before it all fades away is about 10 kilometers. So in a benchtop apparatus, you get about 10 kilometers of optical path length to do your experiment. And the reason the light decays away, it doesn't keep going forever, is because, well, we design this so the light is reflected very carefully backwards and forwards, but no mirror is ever perfect. So the mirrors are 99.99% reflective, but the 0.001% of non-reflectivity leads to light that escapes from between these two mirrors. And so that leads to a decay of the light intensity. So if we plot the intensity of the light that's leaking out through this end mirror here, so we put a light detector, a photodiode, behind one of those mirrors and just measure the intensity of light, what happens is the light intensity decays over time. And it will decay with a pure single exponential decay if we've set the experiment up right. So that's our measurement. We're not going to measure the change in intensity. We're going to measure the time it takes for the light to leak out of this cavity. And the idea is that if we just have an empty cavity with nothing in it except our two mirrors, then the lifetime of the light inside between these two mirrors is just determined by how reflective they are. But if we then put a single particle in the middle of our cavity, and I've exaggerated this so you could see it, but in reality that particle is much, much smaller than the laser beam, then if that particle is scattering and absorbing light, that introduces another way for the light to escape from the cavity. So instead of just leaking through the mirrors, it's also now being absorbed and scattered out of the cavity. And that shortens the lifetime of the light in the cavity. So what we measure is the change in the lifetime of the light in between these two mirrors, and we can back that out, and I won't go through the maths of it, but we can back out this property here from that analysis. It's a very simple measurement. We measure the decay trace here with and without the particle. So the decay gets faster when the particle is in the cavity. We look at the change in the lifetime, and from that we can measure what's called the extinction cross-section, which is a measure of how strongly the particle is scattering and absorbing the light. All right, so that's the measurement. So then we have to somehow hold our particle in the middle of our cavity. So now we have to resort to optical trapping techniques or some sort of trapping method to confine our particle in the cavity. So we can use laser tweezers. We can hold a single particle with a focused laser beam. And this is a technique that's used in lots of areas. There was a group in Bristol, I have a collaborator in Bristol, Jonathan Reed, who was the first person to do this with aerosol particles. It turns out you can't use a traditional laser tweezer to do this because the laser tweezers that are used in biology have a very tight focus and they hold a particle very close to a microscope objective. And we can't stick a microscope objective into our experiment because it'll block our laser beam for our optical measurement. So we use something called a Bessel beam. This is just an alternative form of optical trap. And this is what it looks like in cross-section. So if you look into the beam, which you should never do with a laser, the central core of this is about 5 microns in diameter, and it's a very intense part of the laser beam, and it propagates over several millimeters. So it allows us to trap a particle and manipulate it over several millimeters. So we can levitate a particle using this what's called Bessel beam. So you can see that here. We generate the Bessel beam with a screen laser here. We levitate a particle by trapping it in the middle of this laser beam, and we hold it right in the center of our cavity ring down experiment. And so we hold the particle there. We can trap it for many hours if necessary and just hold it there and measure its optical properties. There are some subtleties to this, but that's what we started doing. And then we can use the light that's scattered from the laser beam to work out the size that, yes. So we do have to worry about the radiation pressure. Partly we're using the radiation pressure to levitate the particle against gravity. So we're exploiting that. What we have to be very careful of, and I'll talk about this in a moment, is if the particle is also absorbing the laser beam, then that heats the particle, and that generates another force that acts on the particle, and that makes it unstable in the trap. So what I'm telling you doesn't work for absorbing particles. So we'll come to that in a second. So we can look at the interference fringes that come from this particle and use those to work out the size of the particle. So that's what's being shown in this picture here. So we've got a camera looking at the light that's scattered from the particle, and these fringes you can see are characteristic of the size of the particle. So we can use that information. But let me hope if this movie plays, if you watch the panel on the right-hand side, this is another way that we trap the particles. So you can see some particles here being loaded into a trap. This is now an electrodynamic trap. So this is using a quadrupole to confine the particles. And you can see a stream of particles has been generated by a dispenser. And those particles are now actually being levitated with electric fields. So they're being confined between 4 charged rods, just like you have in a quadrupole mass spectrometer. And there's a charged plate at the bottom here, which is applying a repulsive force if we put a charge on the particles themselves. And then we can levitate the particles and trap them in a straight line. And we can play around, if I can get this movie to play again, we can then play around with the positions of those particles, and we can manipulate them so that only one of them is sitting in the middle of our spectrometer. So you can see we can dispense them out, we can select the ones we want, and we can control the particles with really high precision. So so we combine that trapping technology with the spectroscopy technology, and then we can look at single particles one at a time. So we put all that together. We measure, so we trap our particle in the middle of this laser beam. And what we do normally is just let the particle evaporate over time. Yeah.
So the particles are charged.
Sorry, could you say that
So
again?
these particles are charged particles.
Yes. So we put a charge on them. Yes. So that we can trap them.
Can you, so you can do this controllably, like you know how much charge is there?
Yes. So in principle, we can work that out based on the voltages that we're applying to levitate them. Yes. I can't tell you off the top of my head how much it is, but we do know in principle how charged they are. Yes.
So basically, so the reason I'm asking is that the Paul trap dynamics depends on what the charge to mass ratio. So are you you're going to be able to trap only one if your mass is constant, only one charge kind of charge. So are you trapping everything or only a fraction of?
Are we what? Sorry, I didn't
Are
quite.
you trapping anything that is getting generated, or do you have control over that, or you know?
So
you are just
we're generating the droplets with what's called a droplet on demand dispenser, which is it's a nozzle which has a very well-defined orifice size. And so the particles that come out have a very well-defined size so drop to drop, they might be tens of microns plus or minus a few nanometers. So they have very well-defined sizes. And then we put a charge on them by passing them past an electrostatic plate. We charge them, and then we levitate. So we can put a feedback loop on the levitating voltage, so that we just stabilize the particle with using a camera right in the center of where we want it. Okay. Right. So what we do is we then let the particles evaporate. So they're going to lose volume. They're going to get smaller. And as they get smaller, we fix our laser beam at one frequency here. As the particles get smaller, they interact differently with the wavelength of light in our laser beam. And they interact differently mainly for 2 reasons. So we get what are called whispering gallery mode resonances in these particles. So if you have a spherical particle and the wavelength of light that you're exciting the particle with, if it were propagating around the outside, sorry, I don't have the motor skills with this pointer to do this very well. If the light is propagating spherically around the surface of the droplet, and as it goes round, when it comes back to where it started from, its wavelength overlaps perfectly what it started with. You get what's called constructive interference, and you get a whispering gallery mode resonance. And those are named after this building in London, St. Paul's Cathedral, which has this dome on the top. And this dome houses what's called a whispering gallery. So if you go into this dome, if you go up and stand in this dome and you say something quietly, the sound waves propagate around the circumference of this dome, and you can hear very clearly on the other side what's being said. So this is, again, a constructive interference pathway of the sound waves propagating around this dome. And the same thing happens in droplets. So this light gets trapped, and this interference gives these very sharp spikes in this measured, what's called extinction cross-section, this thing we measure in our cavity ring-down experiments, which depend critically on the size of the droplet and the refractive index of the medium the droplet is made up of. And then you also get broader interference structures. So you can perhaps see some broader features in this pattern here. And those come from interference between light that goes through the droplet and light that goes round the droplet. Because the light that goes through the droplet changes, it has a different speed as it propagates through the droplet, and so it ends up out of phase with the light that went round the droplet, and that gives you interference structure as well. And so those two added together are all treated by Mie theory, but they give this interference. You get this very structured, it looks like a spectrum, but it's not a spectrum. It's showing you how the light is interfering as it goes through and around the droplet. And if you look at this very carefully, you can perhaps see there are some black points which are experimental measurements, and there are some red curves through that, and the red curve is a fit to Mie theory. So we're fitting to this theory for homogeneous spherical droplets, and we're doing a pretty good job here of capturing all of the structure, and the parameters in that fit are just the refractive index properties of the droplet. So we get a very, very precise and accurate determination of the refractive index from that measurement.
This sigma extension parameter, how should I interpret this? Higher the value, more absorption, or opposite of that?
So it's a convolution of two effects. So it's a measure of how big the particle is. So if you imagine a spherical particle, it's just like the circular cross-sectional shape of the particle. So the bigger that is, the more light it blocks, if you like. So we call that a larger extinction cross-section. But then if the particle also absorbs light, that's blocking more light too, and so sigma also gets bigger. So it's a combination of the physical size of the particle and the amount of light it absorbs.
WGN resonances actually result in
More absorption because they're causing the values
Yes.
to peak up.
Yes.
Okay.
So what they're doing is essentially causing the light to propagate multiple times around the surface of the droplet, and that gives the interference. It's very sharp interference because in optical terms, it's quite a high finesse cavity or a high Q cavity. So you get very sharp resonances. So now let's do that experiment for 3 different particles. So the top one has no absorbing dye added to it. So it's just in this case hexane triol, which is transparent with no absorbing dye. And then the next 2 droplets are ones where we've added some amount of a black dye called nigrazine. So this dye is an absorbing dye. We've added, so this WN number in the pictures, that's the fraction by weight of the dye that we've added to the droplets. So these are very dilute droplets with this dye, but we're adding in absorption now to our particles. And you are seeing that the structure here, this pattern here is changing. And our fits are reflecting that. So specifically what happens is when the droplet gets more absorbing, you lose these very sharp spikes. And that's because the light that's trying to propagate around the surface of the droplet inside it is not getting very far because it's being absorbed. And so the effect of that is, again, in optical terms, is to reduce the Q factor or the finesse of the cavity. And so you're getting a broadening of the resonances, and then they disappear completely. So we can fit these patterns to determine not just the scattering, but also the amount of light that's absorbed by these very small particles. So in technical terms, we're getting both the N and the K components of the refractive index. So this is just to show you we can do this, and we determine, so this is just a measurement for this nigrazine dye compared to what we expected based on the stock solutions we made up, and we get very good agreement in that case. But let me I'm conscious that I'm
Just a
taking
quick question.
Yeah.
The signal to noise in these measurements, what do they depend on?
What it depends on, we've published papers that describe exactly that. It's an important question. What it really depends on, it turns out, is how much the particle is moving in the trap. That's the biggest source of noise, because as it moves into different parts of the laser beam, that actually affects our measurements. So we have to really tightly confine the particle.
WGN, it's very important how we launch the light beam into it. Does that matter? Is your particle really, you said, is smaller than the light beam?
Much smaller.
So part of that light gets trapped, or usually you think of it WGM when the particle is much bigger than the wavelength of light, and you try to launch it so that it
So
Go around.
you would typically edge irradiate a particle if it's a large particle to excite these. Just to give you a sense of this, these particles are about 2 microns or so in diameter. The laser beam focus in the middle of our cavity is about 300 microns. So it's much, much bigger than the particle size. So all we have to do is get the particle dead center in the Gaussian profile of the beam, and everything else takes care of itself.
Okay.
All right, but I want to just get on to these nitroaromatic compounds that I mentioned previously. Sorry, I'm going to try and go the right way. So going back to this brown carbon. So what I showed you there was very much a model system of this black dye dissolved in hexane triol. Can we actually study these nitroaromatic compounds? Now they introduce a level of complexity because these molecules are weak acids. So they exist in different forms in solution depending on the pH of the solution. So this molecule here is called nitrocatechol. And because it's got these 2 OH groups, in aqueous solution, it can lose one of the hydrogens as an H+. So it's acidic, and it makes this anionic species, this phenolate species. And then in principle, at high enough pH, it can be deprotonated twice to make a double anion. And these different species have different absorption spectra. And you can see that here in this row of pictures here. So these are all different, these are all solutions of this nitrocatechol in water, but at different pH. So it's just acting like a pH indicator. At low pH and under acidic conditions, you have primarily this molecule, which doesn't absorb visible light. But then as you go to higher pH, you introduce this form here, which starts to absorb at around about 400, 450 nanometers. So it absorbs blue light, so the solution looks yellow. And then if you go to high enough pH, these molecules will absorb red light or green and blue light. And so the solution starts to look red. So the properties of these nitroaromatic compounds depend very much on the pH. So that's another level of complexity we have to worry about. Those are just showing the absorption spectrum and the changes. So we haven't fully explored the pH dependence yet, but let me show you what we can do with these compounds. So here's a particle that we've created in the laboratory. We've taken an aqueous solution of ammonium sulfate. So we've just added ammonium sulfate to the water to hold the water in place in the droplet, essentially. It's a hygroscopic material, so it just holds the water there. So we can make a droplet, and we've added some of this 4-nitrocatechol, this nitroaromatic compound, and we are then going to levitate that in our trap and look at its optical properties. So here is our experiment where we're letting the droplet evaporate, and actually it's evaporating this 4-nitrocatechol, which is a volatile species. So it's shrinking in size over time. So it's going from right to left as you look at it. Left to right, right to left as you look at it. It's getting smaller. And this is just the ammonium sulfate with a structure here corresponding to the Me theory. And then we add the nitrocatechol, which is now absorbing some of the light from our laser beam. And we see a different pattern of structure in the Me scattering. And we can analyze that to extract the refractive index, both the real and imaginary parts. So the scattering and the absorption parts of the refractive index. So we can quantify, for this 2-micron size particle, we can quantify very precisely its optical properties. And we can make a more concentrated solution of this nitroaromatic species. So the droplet looks darker. And then we do the same experiment. And now you can see we face a bit of a challenge because we've made this droplet sufficiently absorbing that all the structure disappears from this Me scattering. It's all getting washed out by absorption of light in the particles. But even so, we still think we can fit that and extract pretty accurate values of the refractive index of these particles, because we're not just measuring the change with radius of the particle, but we're measuring this absolute property. We're not measuring a relative property, we're measuring an absolute property. We're measuring this extinction cross-section in absolute terms, and that allows us to fit these data sets. So we can still extract, even for quite concentrated, strongly absorbing particles, we can extract the optical properties. These are the numbers. They're not going to mean a great deal, but we do extract. If you look at the scale bars on here, you'll see that the error bars look quite large, but that's because the values are plotted on quite an expanded scale. So we do get very precise, and we believe accurate determinations of these optical properties. And so that's a way we've developed a methodology that can now be applied to other types of atmospheric aerosol. So we can really start to nail down the optical properties of these particles and ultimately, just to remind you, reduce the uncertainties then in understanding how these particles interact with sunlight in the atmosphere. So that's the objective of this. Really what I'm telling you about is a technology that can be used to really address this problem. So I feel like I've already talked for quite a long time and not got even halfway through my talk. I'm going to give you a very short overview of the next step, but Jyotirshman is going to wave at me frantically when I should shut up.
Yeah.
Okay, fine. So what I've told you so far is what happens when the aerosol particles or these nitroaromatics in the aerosol particles, how strongly they interact with light, so how strongly they absorb the light. So the next question is, what can we learn about what actually happens to these nitroaromatic compounds after they've absorbed light? So what photochemistry do they undergo? In essence, what we want to know is, does the energy of the sunlight cause these molecules to degrade? So does it induce some chemistry in them that breaks them down into less toxic, less persistent pollutants or not? And it turns out not. That's the punchline. And I'm going to tell you why. So these particles, so let's focus on this one down here. This is what's called paranitrophenol. So it's para just means the OH group is opposite to the NO2 group in this molecule. This molecule absorbs light at about 300 to 350 nanometers, so in the near ultraviolet. And that corresponds to this part of the solar spectrum. So this plot on the left here shows you the different wavelengths of light that penetrate through to ground level in the atmosphere. So this is light that's come through the upper atmosphere from the sun. It's gone through the ozone layer in the stratosphere. The ultraviolet's been filtered out of it by the ozone layer. And we get down to ground level and we get visible light, which you know gets through to ground level, but also some ultraviolet wavelengths. So these ultraviolet wavelengths here are beyond 300 nanometers, can pass through the ozone layer, and they get down to ground level, and they overlap with the absorption spectrum of these nitroaromatics. So these nitroaromatics can absorb this UV from sunlight, and we want to know what happens to them. So the way we study this is like experiments in Jyotirshman's group. We use a technique called transient absorption spectroscopy. So this is where the ultrafast lasers come in. So we're not currently doing these experiments on aerosol particles. That presents all sorts of challenges. We're starting to think about how we can do that. But what we're doing at the moment is looking at liquids in few milliliter samples. So we would love to be able to do this in an aerosol and see if there's a difference. But at the moment, we're restricted to flowing samples of a few milliliters. So we flow the sample through a cuvette. It's just a very thin cuvette. And we send through an ultraviolet laser pulse to excite the molecules. So the molecules absorb this UV light, and then we come in with another laser pulse to see what's happened. We use the second laser pulse to look at the changes in the sample that were caused by absorption of the first UV pulse. So we call that a pump probe experiment. Pump light excites the sample, causes changes. The probe pulse comes in and looks at what changes have happened. And that probe pulse can either be an infrared pulse. So it might be a broadband infrared pulse of light, again, a very short duration, so only about 50 femtoseconds in duration. Or it might be what's called a white light continuum. And that just means that we have a very short pulse of light, which contains all the colors of the spectrum, the visible spectrum, and some UV light. And we send those pulses of light through the sample, and then we send them into a spectrometer, and we look at which frequencies have been absorbed. So we're taking a spectrum, just in the conventional way, but we're using very short pulses of light to do it. And we're looking at how that spectrum changes when we excite the sample with some ultraviolet light in the first place. What's unusual about this experiment is that we're doing it over a very broad range of times. So in a lab like Jyotirshman's or mine in Bristol, you're probably limited, I'm guessing, to probably a few nanoseconds in time delays, because the way we delay our times in these ultrafast experiments is we use mirrors to send the light on different paths, and it's impractical to send it over very long paths, so you're limited to a few nanoseconds. So if you send, but in these experiments I'm going to show you, we've used a setup which allows us to make the measurements from 100 femtoseconds, so 10 to the minus 13 seconds, out to, in this case, microseconds, which to us is an eternity in this photochemistry. So, and that's done by a very clever arrangement of lasers at the Rutherford Appleton Laboratory in the UK. This is the Rutherford Appleton Laboratory. It's a synchrotron, well, it's a national lab in the UK. It extends quite a way beyond this picture. So Bristol is over in this direction, about 100 kilometers in that direction. London's about 100 kilometers to the left. Oxford's just to the north of this. And this is the synchrotron, but everything we do is in this building here, which looks tiny, but is a very large building because the synchrotron's huge. And so this building houses parts of what's called the Central Laser Facility, which is a national facility in the UK for doing ultra-fast laser experiments. And it's a very useful facility. And I believe that India is now planning to build one of these type facilities in Hyderabad, which will be a fantastic resource for Indian science. So I'm going to focus on this nitrophenol. We've looked at lots of these different nitroaromatics, but I'm going to focus on this paranitrophenol shown in black here. And I'm not going to spend too long on this. I'm just going to tell you very quickly maybe I'll just show you a data set and then I'll tell you what it tells us. So this is the sort of data set that we obtain. So each of these different color traces is a spectrum of our paranitrophenol solution in water at different time delays after we have excited it with some ultraviolet light. And these time delays run from, in this case, 2 picoseconds in blue through the colors of the spectrum to later times out to, in this case, 150 nanoseconds. And these measurements took us about half an hour with this amazing facility. We get all those time delays and many, many more in between, and we get very nice spectra. And there's lots going on in here, but these features down here, this feature here, and this feature over here, are associated with the excited state of this molecule after it's absorbed UV light. So the electrons in this molecule respond to the UV light, they reorganize themselves into a higher energy state, and we essentially taking the absorption spectrum of that higher energy state. And that's what gives these features in the spectrum. And they decay on a few picosecond to nanosecond timescale. But then this feature over here grows in. So this feature here, centered at 400 nanometers, grows in, and then it decays away. And this feature we know is this anion, because we can take a spectrum of this anion in the lab. We can just make that in a basic pH solution and record its spectrum. So we know exactly what that looks like, and it looks like that.
I have a question in the assignment. That is a phenoxide radical, 395.
395
is a phenoxide radical with the 700 feature.
Yeah.
That's typically, if you were to just take the electron and the proton out of it,
Yes.
it should be a radical. It should be the 395 nanometer phenoxide radical.
So
So this is, I'm just
this
sort
feature,
of putting it out that this not just a oxide O minus of proton removed. I think there is an electron removed too.
okay.
I don't know how you make that
So-
sense, but maybe a simple deuterium substitution can enable.
So let me just tell you, we can lift this spectrum out of here and we can overlay it with the anion spectrum, and they're identical. Absolutely identical. I don't have a picture to show you that, but trust me. We, for a long time, thought this was a solvated electron, but it's not.
So there are two features for the
Mhm.
phenoxide radical. One at the pole of.
Yes.
Right.
But the path to the, we have thought about this. The path to that radical requires autoionization, and that is actually energetically forbidden at the wavelengths we're working at. Right. So what we've done is we've then gone back and we've stepped our way through all these different time delays in much more detail to extract everything that's going on. And I don't have time to tell you all this. You're going to have to trust me on this. I'm going to tell you what happens. But we have a lot of spectra that tell us, that pin down exactly what's going on in this system. We identify pretty much every species involved, even though the timescales vary from 100 femtoseconds out to tens or hundreds of nanoseconds. So here's what's going on. These ground states, these are the paranitrophenol molecules. They absorb this UV light, in this case 320 nanometers. They go to what's called a pi-pi star state. So they move an electron from a pi orbital, so a delocalized orbital on the benzene ring, into an antibonding version of that orbital. And very quickly, within 100 femtoseconds, they cross into a different arrangement of the excited electrons. They go into what's called an n-pi star state, and that's the lowest excited arrangement of the electrons in this molecule. And from that, the electrons in that have one spin up, one spin down, and they flip. So one of the electrons flips to spin up. So you got what's called a triplet state, two parallel spins. And so that gets this labeled T1. And normally in organic molecules, that's quite slow, but in this class of molecules, it happens to be very fast and very efficient. So that takes about 12 picoseconds. Then this thing hangs around in the triplet state for about 5 nanoseconds. And then what it decides to do is give a proton to the water that's surrounding it. So it acts like an acid. It's more acidic in the excited state than it is in the ground state. So it gives a proton to the surrounding water, and you make ultimately this. Josh Ishman may not believe me, but that's what we think we make. So we make this anion. And then what happens is that in somewhat acidic conditions, that anion just reprotonates, and you come back to here. So the net effect of all that photochemistry is nothing. Nothing changes. These molecules are stable to UV light. They undergo acidic behavior, so proton transfer to the solvent, but then there's a recovery pathway. And so unless somewhere in here, these can be intercepted by some other chemistry, and they only have about 5 nanoseconds to do that, these molecules are going to recover completely. And we know that from our experiments because we measure, I skipped over the spectrum, but this measurement here is a measurement of the recovery of the ground state molecules. And so this dip, this negative feature is where the molecules have been depleted by the ultraviolet. And as it's filling in here, that's the recovery of the ground state molecules. And it goes back to baseline. It goes back to 100% recovery. So we see that unambiguously. And that seems to be general for a lot of these types of molecule, other ones we studied too. So that helps us to understand why these molecules are resistant to photodegradation in the environment, because they might absorb UV light from sunlight. You might think that that would lead to their decomposition, but it turns out that they have relaxation pathways that just dissipate that sunlight energy as heat, and they just recover the ground state molecules again. So these things don't get photodegraded in the atmosphere. So in technical terms, the quantum yield for the photodecomposition is extremely small. And that is why these and other things like 2,4-dinitrophenols are such persistent pollutants in the atmosphere. So I've gone through that very fast. I apologize for that, but I should just acknowledge key people who've done this work. So the aerosol work was really the PhD work of Jamie Knight, this guy here, who's just finished his PhD, and it's in collaboration with Michael Cottrell, who was in Bristol and has just now moved to a faculty position at Oxford. And they did all that aerosol work that I've shown you. Outstanding people. The ultrafast work that I skimmed over was really done by Debarin. Debarin Ghosh came to me from Sayan Bagchi's lab in Pune, and he's been with me for 2 years now and is a really exceptional experimentalist and has been doing all the ultrafast work in my lab and at the Rutherford lab. And he's been working with PhD student Will Whitaker, but really this is Debarin's story that he's done this work. And you don't care who funds me, but I have to put this on my slides anyway, just for form. So I hope I haven't talked too long. Thank you very much for listening to me.
Thank you, Andrew. This was fantastic colloquium. Thank you very much. Questions? Yeah, let's go.
So going back to the beginning, you spoke about various sources of pollution.
Yes.
What about the wars? The war that's been going on for 2 years.
wars?
Yeah, the war between Russia and Ukraine,
Yes.
and the latest one in the Middle East. What kind of pollution do they contribute, and what type of pollution, and how much level?
Well, the pollution I think we should be worrying about in Ukraine is what happens if their nuclear power stations don't get properly maintained and cooled. Then we'll get another Chernobyl, and that's really worrying. But in terms of the pollution that's generated, I hate to say it, but I haven't seen the numbers, but I suspect that the amount of pollutants being released into the atmosphere from that is probably still less than the effects of international air travel and shipping, which I think are much more significant.
The kind of toxins, the weapons that they use.
Quite possibly. So those may be generating localized pollution. I'm not sure how far it transports. There's also things like depleted uranium, which are used in munitions, which ends up just ends up in the ground near where it's come from. But I don't know, I haven't seen studies of transportation of that pollution, so I can't answer that, I'm afraid.
Slightly different from the talk, but what I was thinking about is that your whispering gallery modes are in some sense analogous to the Etalon, Fabry-Pérez
Yes,
Etalon.
absolutely they are, yes.
And I have a young colleague here sitting over there who looks at chemistry within the Etalon where the cavity modes couple to the vibrational modes of the molecule. And here, if I calculate it, if you're taking the WGM, they're about 3 microns, for a micron diameter, 3 microns, which can couple to some of the vibrational modes.
Yes.
You see any effect of that in particular sizes? Anything changes, the chemistry, the absorption, the production of any new molecule?
So, all right. So I think what you're talking about is the idea of polariton.
That's right.
All right.
Talking about the polaritons.
So generally, just to be clear, the cavities we're making, we'll talk about the droplet in a second, but the cavity itself is way too big to induce polariton effects. So polariton effects need a microcavity. So then the question is the aerosol droplet itself a microcavity, and does that generate polariton modes? I don't think the fields that we generate in the droplets are high enough but I haven't done the calculations. But I think people are looking at polariton effects in spherical resonators, if you make them small enough. So that is an interesting question, whether that might actually influence things. Yeah.
Just a quick question. So you said that the evaporation rate of your droplets, like, do you control the evaporation rate, or it's just what you get?
If it's something like hexane triol, we can't really control it. We just go with, we essentially choose a solvent which evaporates at a rate that is good for our experiments. If it's water evaporation, we can control it because we can control the relative humidity around the droplet.
Okay.
So we use a dry nitrogen flow, we humidify that in a controlled way, and that controls the rate at which the size changes.
Okay.
So it depends, but we don't want to fill the lab with hexane trials, so we don't do that.
I see.
Okay.
And that's related to that. I mean, that probably causes the jitter of the position. Like as it changes the size, you have to actively do some feedback to put it in the exact.
So we have a feedback loop. It turns out in our traps, we studied this quite carefully. In the optical trap, the Bessel beam trap, the core of that is only 5 microns across, and that turns out not to matter too much, that sort of motion. But in the electrodynamic traps, the particle moves about 40 microns. There's a driven motion of the particle in these quadrupoles, and that gives about a 40 micron motion, and we can't reduce that unless we redesign our whole traps system. And that 40 microns matters because it's getting to be similar to the size of the laser beam in our experiments. So our laser beam is 300 microns across, and that starts to matter.
I see. Thanks.
Question?
So in the second half, the last slide you showed about the fact that the UV leads to certain reactions, but the system comes back.
Yes.
So during daytime, when the sunlight is always present, so these molecules are continuously doing this dance all the time, and they're going back and
Yes.
through this, or do they reach some kind of steady state where they don't stop changing? Or
No, they will continue to cycle around. Now, quite how frequently they do that, I haven't done the maths of that, because it depends on how strongly they absorb light. So the probability of them absorbing a photon is quite low in the first place. So they're not all the time doing this, but they will probably cycle maybe a few times a day. I don't know. But yes,
sorry, why do you say few times? Some of the timescales are all in nanoseconds, right?
Right, but we're only looking at the molecules that we happen to excite with a laser beam. So the flux of sunlight is much lower than our laser beam.
Okay.
And so maybe 1 in 10,000 photons is absorbed. So the flux is just much lower.
But the quantum yield you would know, right? The quantum yield of generating, and then you can calculate a photostationary state
Right.
for the
So what
fraction.
So I'm not sure if the quantum yields are known for the triplet state. It's going to be,
we don't know.
but they're known for the photodegradation, and they're sort of 10 to the minus 6 for the degradation.
Okay, just a very quick follow-up because I'm not a chemist, but so these reactions are of course stochastic processes, right?
Yeah.
So when you say it's something hangs around for 5 nanoseconds, what is the plus minus there typically for these
So
kind of
that's
reactions?
like a half-life.
Okay.
So it's a 5 nanosecond lifetime defined as first order kinetics. So
Got
it's a
it, got it.
half-life.
Thanks. Yeah.
Just a quick question, a bit naive. Do you foresee any clustering or dimerization, especially with your second project in terms of how that would affect the recovery?
So
If you have
do-
hydrogen bonding, for example, or some sort of an aggregate forming.
So we do worry about whether these things aggregate in solution, yes. So we work at sufficiently low concentrations that we believe that any quantity of aggregate is minimal in the system, but this is a worry. And a lot of these organic compounds do aggregate in water, yes. So we have to be alert to that, yeah.
Just, you know, intuitively, what do you think that would do to the recovery of the ground state if the concentration was high enough?
So where that gets interesting, I think, is if this is actually in a real aerosol particle, where we're not just a dilute solution in water, but you've got other organic species. This triplet state here, if it is living for 5 nanoseconds or thereabouts, there is some chance it could do some chemistry. And that will be enhanced if it's adjacent to a molecule, if it's conveniently aggregated. So that then is another area of study for us, is then if we do induce aggregates, does that start to introduce some photodegradation pathways? But we don't know the answer to that yet.
Are there any questions, further questions? Well, if there are none, let's thank Andrew once again. This was fantastic colloquium, and thank you all for coming out today and playing by the new rules. So thank you.
My pleasure. So we look very carefully at tunnel liver. Yes.